I'm Paula. I'm supervised by Ivor and a second-year PhD student, and I'm interested in computer vision problems where we have some type of low-level data representation, like pixel values in images, and then we're trying to understand something based on that data or do some sort of modeling or analysis. And this is relevant in lots of different domains, like medical imaging, but also robot vision or even audio analysis. And one thing that is central here is a distance function that quantifies the similarity between images. And so I'm interested in finding a perceptual metric that is giving us some sort of score function that characterizes similarity. And this is relevant both as an evaluation metric to kind of look at models and compare to some type of ground truth on how well they're performing, but also as loss function, where the similarity scores are essentially driving the learning of our models and are very relevant in these downstream applications. So I'm particularly interested in finding metrics that align with human perception, and I'm going to go more into what that means later, but also in models that are both interpretable and robust. Because of reasons you heard before in the panel discussions, we kind of need to know what specific features drive our decisions in order to apply them in domains such as medical imaging. So I think my whole lab is a bit sick of me showing too many frog images. So here's a very cute picture of my dog Charlie seeing snow for the first time in Berlin instead. And I applied some small pixel level transformations on this image. So these are slightly rotated, shifted, or translated versions of that original image. And if I was to ask you whether they look the same or they look similar, you would probably not be able to see a difference. So we would say that these types of structured transformations are invariant to human perception, and we need our metric to capture that. On the other hand, we can apply other pixel changes in that image. For example, in the example in the middle, I just applied some small local color changes, and Charlie now looks more like a zombie, I think going a bit manic from all the snow. Whilst on a pixel level, this might not be a bigger change than the examples on the left. To human perception, they're very distinct and they're perceptually distinct. And we need to, in some way, make our model learn the difference between these different types of noise. So what noise we want to be invariant to and what noise is perceptually distinct. And if we look at existing methods, pixel-wise metrics such as SSIM or mean-squared error that you might have used before fail at recognizing that difference. So in the example on the top here, humans were asked which one of two patches is closer to the reference image in the middle. And we would all agree that patch 1 is closer to the one in the middle, whereas these pixel-wise methods would say that patch 0 is closer, maybe because on a low-level pixel scale there's less of a change. So we sadly fail, or these metrics fail to align with human perception, so they can't see. On the other hand, the researchers then came up with very complex deep learning-based methods to quantify perceptual similarity. The main one is called LPIPs. However, these are essentially black boxes, so they rely on deep feature representations and are then trained in quite a complex way based on the classification task in order to match human judgment. However, because of the high complexity of this and they lack interpretability, as we can't see which specific features drive specific scores or determine decisions, and also they lack robustness. We lose all our strength. As you can see a failure case here on the left where the the first example is being judged as very similar. So we came up with something that we called SUSS, the Structured Uncertainty Similarity Score, using machine learning to probabilistically characterize images based on these invariances. So we're trying to learn some representation of the images in different perceptual components in order to learn which types of structure are invariant to human perception. So we kind of wanted to build this probabilistic representation of the space of images and where Charlie still looks the same. and then measured the distance between these representations. And we use something called structured uncertainty prediction networks for that, in order to learn the structures that are relevant for human perception. I'm happy to go more into the model architecture later, but let's get into some results. So firstly, we looked at like classic benchmark perception tasks where humans were asked to perform this classification, which one of two distorted images is closer to a reference image. And we showed that SUSS did indeed perform better than these pixel-wise metrics. So we learned some sort of relevant perceptual structure. And we also looked specifically at these types of transformations and looked at transformations that weren't part of our training. And we saw that it could capture the invariance to structured transformation quite well. And then more importantly, because of its formulation, SUSS is fully interpretable, so we can see on a pixel level which specific features are relevant to the score output and to what extent. And we can basically plot these explainability maps on the bottom here that show, for example, the added spider is the main difference in the first example. We can talk as well. And there's other ways. So because we're learning this probability function over the different perceptual components, we can also sample from the learned representations and see what types of variations are being learned as perceptually similar. There you can see some of these samples. And then lastly, we performed like some small optimization tasks to show whether SUSS is robust or not. And in this example, we applied some transformations to this bird image and then tried to recover the original image by optimizing it based on different similarity functions. So we used LPIPs, but also SUSS to maximize the similarity between the output image and the reference image in the beginning. And we showed that whilst LPIPs wasn't really able to go back to the original image, and with SUSS we could uncover the transformation perfectly. And so that in some way shows that the loss landscape that we're defining through our function seems to be quite nice to optimize. Strong as well. So yeah, in conclusion, this is Charlie, and Charlie is not very happy and very strong. And we've shown that so SUSS has lots of properties that seem to make it really good as both an evaluation metric, but also as a perceptual loss function. If any of you are interested in being as strong as Charlie, feel free to reach out. Any questions?
Hi, Paula. Do we have any questions for Paula? Jamie at the back, can you shout, or can I ever get there quicker?
You can only dream of being as strong as Charlie, but could you use this in like an autoencoder to make perceptually invisible image compression? My question.
So use that as the loss function in an autoencoder. Yeah, I think definitely. One thing that we have actually tried as well using SUSS as a loss function was for a generative task for image super resolution. I think I have some slides on that somewhere. Here, I mean, you can't really tell the difference here, but we did show that you can basically make models learn some sort of structure that is seems to capture what humans find relevant quite well, or like what details are relevant to humans here.
Thank you. Any other questions? I have one question. I wanted to turn it around and say, are there any applications where it would be useful, do you think, to be able to detect differences that maybe humans aren't aware of within images and things like that? So I see this is all great work on kind of the perceptual, the human perception, but are there other kinds of applications? I'm just thinking. I'm not. It's not a trick question or anything like that.
Some way of finding invariances that we don't know about.
Yeah, so that a human wouldn't be aware of if a human, but there was variances.
I think it kind of like depends on our definition of like what humans are aware of or not, but because we are not learning the specific invariances, but we're rather learning some sort of structure that we're capturing at this like probability distribution, we could use that in some way to like understand a wider range of invariances learned by this model. So I think sampling is one way of showing like the different variances that are being learned as perceptually similar. I guess more looking into that.
Thank you. Thomas.
Time for one more.
One more.
Okay, yeah, I was wondering, I mean, how far is this similarity score going? Is it also going to help with 3D views? I mean, so if it was rotated in 3D or was, you know, slightly deformed or something like that?
Yeah, I think we could definitely in our code we can extend this to 3D images. And we did also look into rotations. At the moment, it's only 2D images.
Okay, thank you, Paula.